Welcome to the SAP Tech YouTube channel. Today, we will discuss the fundamental principles of SAP HANA and the architecture of in-memory databases. At its core, a database is a software system designed to perform three functions: organizing data in a structured way, securing it against threats, and retrieving or inserting data instantly. Most computer users save data in a standard file system, like a C drive. These systems rely on sequential reading. If you need the 10th file in a folder, the system scans files 1 through 9 before reaching your target. As a business scales, this linear search creates a significant drag on performance. Avoiding this sequential crawl is the primary reason enterprises invest in database software. They pay to organize their data so the system can bypass the scan and jump directly to the specific information required. To understand why even dedicated databases slow down, look at the physical path a processor takes to find data. A query checks the CPU caches, moves to the physical RAM, and if the data isn't there, finally drops to the hard disk. The limit here is physical capacity. An enterprise database might hold a terabyte of data, but the server's high-speed RAM can typically hold a fraction of that, such as 256 gigabytes. The remaining data remains on the disk. When the processor searches the RAM and fails to find the data, it triggers a mishit. The system must then travel to the mechanical hard disk, locate the data, and push it back up into the RAM before it can be processed. This round trip creates the latency users feel as lag. The hardware solution to this latency is an in-memory database, a configuration where 100% of the business data resides in the RAM, removing the hard disk from the active search path. However, RAM is a high-speed device with a high price tag. Purchasing enough physical RAM to house a raw terabyte of data is economically unfeasible. Making an in-memory database viable requires a software-driven approach to data volume. SAP HANA manages this cost by shrinking the database before it enters the RAM. It does not simply copy the raw files. It reduces their size through compression. Through dictionary compression, HANA replaces repetitive character strings with small integer IDs. Instead of writing finance 500 times, it records a simple number, 2. This reduces the data footprint across billions of rows. A 1 terabyte database condenses into roughly 300 gigabytes. Because the data is significantly smaller, it fits within the 256 or 512 gigabytes of RAM on a standard server, aligning with a realistic budget. Beyond saving space, HANA changes how data is organized. Traditional databases use row store tables, which read data horizontally. HANA primarily uses columnar store tables, organizing data vertically. Built for analytical speed, to calculate total salaries, it isolates only the salary column, ignoring names and IDs, processing math directly from that vertical slice. Since HANA performs these calculations in fractions of a second, it removes the need for aggregate tables, pre-calculated tables used by older systems to store the answers to common mathematical queries. By calculating results on the fly, the system increases retrieval speeds, while simultaneously freeing up more RAM that would have been occupied by those redundant aggregate tables. There is a trade-off. While columnar tables are highly efficient for reading data, they are technically difficult to update. Writing new data into a compressed columnar structure is a resource-heavy process. HANA manages this by splitting memory into 2 zones, a compressed main storage for existing data and an uncompressed delta storage for new entries. Any new record, like a new sales order, is written into this uncompressed space. With no compression overhead to calculate, the system records the data immediately. When you query the database, the system pulls from both zones at once. It scans the main storage and the new delta storage to provide an accurate, real-time result. To maintain efficiency, HANA performs a delta merge. The system periodically compresses the new data in the delta zone and seamlessly integrates it into the main storage, clearing the delta zone. This split-zone architecture ensures that columnar read performance remains consistent without hindering the system's ability to handle high-volume write operations. Since RAM is volatile memory, a power loss would theoretically wipe the entire database. To prevent data loss, HANA uses persistent storage. While all active operations occur in the RAM, the system continuously saves a backup copy of the data to standard hard disks. This persistent backup affects how the system starts. When a HANA server boots up, it must load the dataset from the disk into the RAM before it can begin processing, a phase that takes longer than a traditional database startup. Once that data is loaded, the system operates with a consistent 100% hit ratio. By resolving every query within the RAM, the system eliminates the delays inherent in hard disk retrieval. SAP HANA combines compression, its columnar architecture, and delta merging to provide a system capable of real-time enterprise computing. Please check the detailed information in the description of this video. And if you enjoyed this video, don't forget to subscribe to the SAP Tech YouTube channel.